All right, so what we're going to do is a problem that looks a lot like the one. Well, where's the? There it is. Okay, so what we're this is not the problem you're going to do for the quiz, but it looks a lot like the problem you did for the quiz. Okay. On the quiz you're going to be doing, you're looking at the behavior of ice cream. And ice cream is just in a container inside another container. Okay. All this is a piece of metal inside water. So it's kind of it's the same thing. All right. The pattern is the same. What we have in this problem is we've got a container of water. Okay. So there's water in here. Let me get. There's water in here. Okay. Let me give you the camera view of this. All right. So there's our container of water, and we're putting this metal in here that right now is a liquid, and it's going to solidify. That's what we're trying to get it to do. So let's go back here. Let me find the problem again. That's not it. Where are we? There it is. So it says Wood's metal has a melting and freezing temperature of 70 degrees. So I'm just going to say call it Wood's metal. Has a let's say temperature of freezing is 70 degrees C. Has an enthalpy of fusion. Now fusion is the point where it either melts or freezes. 39.7 joules per gram. Then our water that we're going to put it in, it's we have, let's see, how much of that metal do we have? 12 grams. I didn't put down 12 grams, so I'm going to put 12 grams of our metal. Our water then, well, you know that we don't need to know the freezing temperature of water. We know its original temperature, starting temperature, is 20 degrees C. We have, let's see, 30 grams of water. And the specific heat of water you should know from all that stuff we did yesterday and the day before. All right, what's the specific heat of liquid water? If it's at 20 degrees, it's liquid, right? Between 0 and 100. So what's the specific heat of water? Yeah, that's the heat capacity of water. 4.18 what? Times grams, okay? Huh? Yeah. Heat capacity of water, of liquid water. Okay, because remember, frozen water has a different heat capacity, and steam has still another heat capacity. All substances have 3 different heat capacities. All substances have different heat capacities from everything else, from all other substances, and they all have 3 heat capacities. Yeah. You have a question? No? Okay. All right. So one of these is going to freeze. Which one's going to freeze? The metal. If we're just talking about it freezing and we're not changing the temperature of it, because remember in our graph, that's the place where it has a plateau, right? Look, if you look at the graph, you remember that? Yesterday we talked about this. You have a plateau where you go through the freezing or you go through the boiling process. Okay, and so the temperature doesn't change. Temperature doesn't go up. All we do is add more heat energy to it to get it to melt, or take energy away from it, heat energy away from it to get it to freeze. Look at the graph. Don't just take my word for it. Look at the graph and figure it out, okay? Are you looking at your graph? You got your graph in front of you? This stuff can help you if you're visualizing what's happening. Huh? You can use that if you want to on the quiz. Sure. Okay? All right. What equation do you use? There's only 2 equations that we use to figure out what happens with temperature as you add heat. Okay, there's only 2 equations. All right? Now there's different heat capacities and different enthalpies of fusion, or enthalpies, really. But there's only 2 equations. Look at the equations. There's 5 equations on there, but 3 of the equations are exactly the same, and 2 of the equations are exactly the same. You see that? Okay, so which equation do you use when you're changing physical state? Okay, that triangle H is the change in enthalpy. We talked about that again yesterday when we were looking at let's see, what are they called? reaction energy diagrams, okay, and catalysts. All right. So that equation for this, when it's going through a physical state change, must be what? Well, the value will be negative because you're taking the heat out, right? But what is the equation? If you're changing the physical state, what's the equation? No. What's the equation? Not the value of some something, but yes, I'm asking you to put it in new terms now, in terms of this. This is going to change its physical state, so what equation do we use to calculate the heat change when this is going through physical state change? Well, let's put in just the symbols right now. So it's mass delta H, because there's no temperature change. If we use the other equation, you have to have a temperature change, and this thing doesn't go through temperature change. It only goes through physical state change. Okay? So this is what we're going to use for the Woods metal. So what equation are we going to use to calculate the heat that the water is going to absorb? Right, so the water is going to change temperature. All right, it's going to absorb heat from the Woods metal, okay, and it will change temperature because it's going to stay in a liquid state. It's not going to change physical states. That makes sense? So all I have to do is calculate this and calculate this. Can you do that? I've been doing that for like 4 days because I gave you a homework practice problem to do distribution, right? Tell me how much heat is being lost by the Woods metal, how much heat is being gained by the water. That's the first thing you have to answer. All right. So since the Woods metal is being frozen, heat has to be removed from it. If you're removing heat, the delta H goes down. And the sign of delta H has to be negative. So when we put this 39.7 joules per gram up here into this equation, it really needs to be negative and not positive. Okay, so when we plug in this delta H here, that delta H becomes negative because we're removing heat to make this freezing happen. That makes sense? So now this times this gives you a negative 476.4. Is that what you got? All right, what do we do to simplify the equation? Huh? We're going to simplify first. Cross out the grams, and that leaves us with joules. We still need to round off to how many digits? 2 digits. So we're going to underline this last digit here and simply round it off to 476 joules. That's how much energy, negative 476 joules, is lost by the Woods metal. That's how much energy is lost by the Woods metal to completely freeze the whole sample. Right? All right, so the water down here then. Since water, huh? No, because you have to write it in scientific notation when you have to remove a digit in the ones place. We're not doing that here. You can write it in scientific notation. Nothing wrong with that. I'd give you full credit for it if you wrote it correctly, but you don't have to. You only have to write it in scientific notation when it's necessary to remove a digit in the ones place. Now, it's a lot more convenient to write it in scientific notation if you have really, really small numbers or really big ones. Okay? But the requirement is only when you remove digits in one place that you have to write it in scientific notation. Now, the water then is going to change temperature, and the equation you use when you're changing temperature, this is only a physical state change here, so there's no change in temperature here. You know, we're only changing from liquid to solid for this, right? That's what that equation is. Down here, we're changing the temperature. So we're putting this Woods metal into a sample of water, and the Woods metal is going to freeze. Okay? And so the water then is going to change its temperature. Now the reason we use 70 degrees as our final temperature is because if the water temperature gets above 70, then you can no longer freeze the Woods metal. Okay? The Woods metal freezes and melts at 70 degrees. So the only reason we're using 70 degrees as our final temperature is because you can't go past that. If the water gets above 70, if it gets up to 80, for example, then it's too hot for the wood's metal to freeze anymore. The wood's metal is going to stay a liquid. That's the only reason we chose 70 as our final temperature here. What? Yeah, I thought you had a question. No. Okay. So that means that our maximum temperature change is 50. We're starting at 20. We can only go as high as 70, so the maximum temperature change is 50 degrees. All right? If you go beyond 50 degrees temperature change, we can't freeze the metal. Not completely, anyway. So we had 30 grams of water. That's what we put in here for mass. The specific heat of liquid water is 4.18 joules per degree C per gram. And the temperature change we're looking at is this maximum 50 degrees. Okay? We're adding heat, or specific, well, actually this doesn't change its sign. This might change its sign. But this is positive because we're going to end up with 70 maximum, starting at 20. That's our initial temperature. Remember, change in temperature equation is temperature final minus temperature initial. So our initial temperature is 20. The final temperature that we can get to, if we're still going to freeze all the wood's metal, is 70. So that means our 70 minus 20 is a positive 50 degrees C. Plug that in. How do we simplify the equation? Okay, cancel units. All right. Multiply. Everything's on the top here. All the ones on the bottom, that's just ones. You divide or multiply the ones, you get the same number. So that'll give us 6270 units of joules. And joules measure heat energy. Both times we've got joules as our heat energy. Okay? So we know we've set it up right if we get the right units. Well, there's a really good chance we've set it up right if we've got the right units to measure what we're trying to measure here. Okay? So the water can absorb up to, for this temperature change right here, the water can absorb up to 6,270 joules. Now, I haven't rounded it yet. Okay, I need to round it, but let's just leave it there for right now just to look at it. Okay? Is there enough heat capacity to completely remove this amount of heat from the wood's metal and freeze all of it? Yeah, absolutely. Way more than enough. 10 times, well, actually, more than 10 times enough, right? Like 12 times more than you need. Got it? That's all you got to figure out. So don't make it harder than it has to be. The math is easy. It's plug and chug math. You got to figure out which equation goes where. If you're changing physical state, it's this equation. If you're changing temperature, it's this equation. Then you got to look at the numbers over here and say, okay, this is the wood's metal. It's changing its physical state, and it's got to give away this amount of energy in order to completely freeze. The water has to absorb at least that amount. So as long as the water energy that it will absorb is greater than or equal to the absolute value of this, because it's got to be, this is negative, this has got to be positive. Okay, as long as the absolute value of this is less than or equal to the amount of heat the water will absorb, it'll freeze it when it reaches equilibrium. Does that make sense? Don't make it harder than it has to be. Okay? The math is easy if you can just figure out which equation to use. And you shouldn't have a hard time figuring out which equation to use because there's only two and they go to specific situations. You got to figure out which situation it applies to. Are you changing state? What are the physical state changes? One of them is freezing. And what's another physical state change? Huh? Water's a substance. It's not a physical state change. I'm looking for a physical state change. What is another physical state change? Freezing is one. What's another one? Melting. Good. What's a physical state change? Yeah. Boiling. What's another physical state change? Michelle. Condensation. Okay? If you're changing physical states, what are the three physical states? Liquid, solid, and gas. There is plasma, but that goes beyond what we're working with here. No, plasma actually, with plasma you actually separate the electrons from the nuclei. And we don't, that's not where we're going. You no longer have really water, or you don't have compounds anymore. Okay? You don't have substances as we could think of them when you do get plasma. So plasma is a physical state, but it's kind of beyond what we're working with here. We're working with three physical states right now. Okay? solid, liquid, and gas. If you go through a physical state change, how do you get there? That's all you got to know, right? How do you go from liquid to solid? Freeze. How do you go from solid to liquid? Melting. Right. And it doesn't matter whether it's water. It could be anything you're melting. How do you go from liquid to gas? Boil it. How do you go from gas to liquid? Condensation. Okay, that may be the only term you probably aren't familiar with. All these other terms you know in your everyday life, right? Okay? Condensation really is used in a couple different ways, but the term we use for going from gas to liquid is condensation. Okay? You just got to choose which of those equations fit the physical state change. This is the only one that goes through that is the physical state change. It's the first one here. If you're boiling, you use this. If you're condensing, you use this. If you're freezing, you use this. If you're melting, you use this. Got it? All the other things that happen, if you're changing the temperature of something, that's this equation, because there's a change in temperature term there. You've got to figure out which one fits, choose the right one, do the math, and then figure out how do we use this information. The water can absorb enough heat. You got it. Because that amount of energy change. Now, of course, remember I didn't put this in scientific notation yet. You're required to do that. Okay, but I just kept it there so it's easier to see how the two relate. Okay, I need to round this off to 3 digits. Huh?